Welcome to this video on finding uncertainty from a titration. This is the third in a series of videos on error and uncertainty, and this one we're having a look at a concrete example of how we can put what we've learned in the last two videos into practice in the context of a titration experiment. So imagine that you've done this titration experiment. You prepare a standard solution of sodium hydroxide, you add an unknown concentration of hydrochloric acid until your indicator changes colour, and then you determine the concentration of the hydrochloric acid to be this value here. And I've deliberately left this as an unrounded value because we don't know how many decimal places to give this to, based on the fact that we don't actually know what the uncertainty is for that experiment. Do we know it to 5 decimal places? Do we know it to only 1 decimal place? Well, it depends on the equipment that we've used. So the equipment that we've used to make our standard solution, we used a 2 decimal place balance to measure a certain mass of sodium hydroxide. We then used a 100 centimeter cube volumetric flask. In the titration, we used a 10 centimeter cube volumetric pipette to take out a portion of our standard solution, and then we used a burette to measure the titer, which was 8.35 centimeters cubed. So if you've been watching the last two videos, it would be interesting to see if you can manage to calculate the overall uncertainty, and that would be a value in centimeters cubed, in moles per decimeter cubed, for the overall uncertainty on that test result there. So can you see if you can have a go at doing that? Pause the video and see if you can do it. Well, let's see how you got on. So you start off with the absolute uncertainties. 2 decimal place balance, it's plus or minus the resolution. The next two bits of kit, it tells you exactly what the uncertainties were. And in the case of the burette, it's plus or minus half the smallest graduation, so half of 0.1 centimeters cubed. But then we need to double that because we took 2 measurements with the burette, the final reading and the initial. So we need to double the absolute uncertainty. Then you next find the percentage uncertainties using the formula shown at the bottom. And just a reminder of the way you might have tripped up was that when you were doing the burette, the measured value is the titer, not the final or the initial reading. Then you sum up the percentage uncertainties to get the total percentage. Turns out to be 4.3%. And then you divide that value by 100 and multiply by the test result to get an uncertainty of plus or minus 0.05157 and so on and so forth. So what are you going to quote your concentration to be? Well, first you deal with the uncertainty. You say, well, the uncertainty I'm going to quote to 1 SF, and unless this figure is a 1, that's always what you do. If you happen to get 1 as your first figure, then you would quote it to 2 sig figs. So plus or minus 0.005 moles per decimeter cubed is my uncertainty. Now that means that my test result is varying in the 3rd decimal place. And so I'm going to quote my test result to 3 decimal places, which would be 0.120. Now this is a little bit different. In these experiments you tend to conserve significant figures if you were doing this without uncertainties. But here we just use decimal places, because what we're basically saying here is that this 3rd decimal place is variable, and it's subject to a variation of 5 within that, or 5 thousandths. So there's no sense in quoting this to more significant figures, but equally we don't want to quote it to any less, because we want to know what is the range of values that this actually corresponds to, and so we need to know what this number is in the 3rd decimal place. So you can use this to work out if there are any systematic errors. This is my experimental result. So rather than just having a sharp value that I said the concentration was 0.120 moles per decimeter cubed, now I'm saying it's going to be somewhere between 0.115 and 0.125. Do we have a systematic error present? Because remember, this is only a measurement uncertainty from random errors. Well, it depends on what the true value is. So let's say we have the true value of 0.122 moles per decimeter cubed. That's going to lie somewhere in here. This would be case number 1. And in that case, our true value lies within the bound created by our uncertainty, and so there we've got no systematic error. In the case 2, let's say our true value happened to be 0.11 moles per decimeter cubed, which is over here. In that case, the true value is outside of the bound or the range created by our uncertainty estimate. And therefore, the additional source of error, which is this here, is got to be due to some kind of systematic error. So there we would say that we do have a systematic error present. Now it's possible that there's some kind of measurement uncertainties we haven't accounted for, and so there are actually more random errors that we think. But generally, if the true value lies outside of our range that we've created by taking account of the measurement uncertainties, which are essentially the random error estimates, then we must have a systematic error present.